Okay, it's been recorded, and well, I have the honor to introduce Magnus. I don't think he needs to be introduced. He's so well known in the community, but just for completeness, I'll give a very short introduction to him. So he's currently dean Dean of Engineering in the Samuli School of Engineering and a professor of Department of Electrical Engineering and Computer Science at UC Irvine. Prior to that, he was on the faculty of Georgia Tech and serving as a school chair in School of Electrical and Computer Engineering and the director of Georgia Tech's Institute of Robotic and Intelligent Machines. He received his master's degree in engineering physics and a PhD degree in applied mathematics from KTH, Sweden, and a BA degree in philosophy from Stockholm University, and then worked as a postdoc scholar at Harvard University. So he conducted research in the area of control theory and robotics, with particular focus on control and coordination of multi-robot systems. He's a fellow of IEEE and is the president of IEEE Control System Society. He's a member of the Royal Swedish Academy of Engineering Science and has received many awards, including teaching and research awards, for example, Roxini Education Award and Hugo Shank Best Paper Award. I'm not going to read all of them. So today he'll be talking about constraint-based control design for short and long duration autonomy. So during the talk, if you have any questions, you feel free to type in the chat window. And I think we'll have a question and answer session in the end, if that's okay with you, like that.
Absolutely.
In which case, without further delay, time is yours.
Thank you. Thank you so much, Bing. Let me see if I can share my screen properly here. So,
yeah.
Does it work?
Yes.
And do you have presenter view going?
Yes. Yeah.
Excellent. So thank you so much for this kind introduction, and also for inviting me. I think one of the positives, if there is such a thing, of what has happened during the past few years is that it's possible to connect across the planet in real time and travel to Southampton and give a talk on long duration autonomy, for instance. And what I'm going to do today is talk about this idea of autonomous systems deployed over truly long timescales. And what I mean by that is systems that are out for months doing something potentially useful. And the question that I'm going to ask is there something different fundamentally in how we should think about the control design for these systems? Of course, if you're deploying a robot, let's say on Mars for 14 months, yeah, you got to do some serious ruggedized engineering. Your electronics need to be stress tested and deal with temperature variations and so forth. But from a control design point of view, is there something that's different? And I'm going to claim that there is. This is also closely related to what's referred to as assured autonomy. So these are now systems that are out, that are learning or evolving or adapting over time, but they need to do this in such a way that we can actually trust what's going on. And one of the things that controls, I think, brings to the table so well is we have tools that mean that we can trust what our systems are doing. If I throw a deep neural network at a system, something comes out, but it's very hard to have guarantees for behavior or that you can actually trust what's going on. But with the introduction of controls into these systems, all of a sudden, we actually have systems you can rely on. So that's the overarching theme. And here's the most canonical of all autonomy problems. It's don't hit stuff. Don't run into things. It seems rather rudimentary, but it's actually a hard problem to solve. So this is the 2007 DARPA Urban Challenge. So this was 15 years ago. There was no such thing as a self-driving car back then. People had started thinking about how do we do it, but there were no companies. Google X didn't exist, certainly none of the startups we know now. And the idea was, can we build autonomous vehicles, cars that could drive with other cars? And on the left, this is I think, the most famous robot collision yet that has happened. It's the MIT self-driving car and the Cornell self-driving car. No one is in the car, and the car collided. And people are still arguing over who is really at fault here. Doesn't matter. Point is, 15 years ago, we didn't know how to avoid collisions. I had a car also in the Urban Challenge, and we did really well. We made it to the semifinals, and then in the semifinals, this happened. This is our car. It's a Porsche Cayenne that's beautiful, and we drive straight into a wall. I don't know if you can see it, but basically, we collided. We also put a very expensive piece. It's called a Regal laser scanner as a bumper up front. So that was maybe not the smartest design choice. The point, though, is collisions in 2007 was something we didn't know how to deal with. If you fast forward to today, right, there are tons and tons and tons of companies that have grown up now dealing with autonomous driving in different forms. Every major auto manufacturer, more or less, they have an autonomous vehicle division. There is a full kind of secondary ecosystem that services different layers in the autonomous stack. You have sensing companies, you have communication companies, you have learning companies, you have interface companies. So we now have a much, much more robust and mature understanding of course, how to think about autonomous cars. Despite that, the fundamental problem of don't hit stuff is still not solved. Autonomous vehicles still hit stuff. And why is that? Well, there's something that autonomous vehicle people talk about that they call the 100 million mile problem. And it really is a variation of the following observation, that roughly in the US, and these numbers are more or less the same across the planet, every 100 million miles, there is a fatality in traffic when the cars are piloted by human drivers. And in the US, that translates into roughly 30,000 deaths every year in traffic. So 30,000 deaths. Let's say that we tomorrow magically woke up and we had 100% self-driving vehicles instead of human piloted vehicles. Well, these vehicles clearly need to be as good as the human piloted vehicles, which means we should not have more than 30,000 deaths in traffic every year with our autonomous vehicles. But if we had 30,000 deaths, no one would be okay with it. The headlines in the newspapers would be, robot cars kill 30,000 people. No one would be comfortable with that. What if we were twice as good? What if our autonomous vehicles were twice as good as the self-driving car, as the human-driven cars? That means the robots only would kill 15,000 people in traffic. Again, we would not, as a society, be okay with 15,000 deaths caused by robots. What that means is that the bar is so much higher for autonomous vehicles than for human piloted vehicles. It's not even clear that we would be okay with 10% of the deaths. Would people accept that robots killed 3,000 people in traffic? Unclear. What is clear, though, is that autonomous vehicles must exceed this 100 million miles between fatalities. And the problem now is there's a lot of weird stuff that happens during a 100 million mile journey. You may think that obstacles look a certain way, and all of a sudden there are holes in the road, or cows, right? You're going to experience all sorts of strange weather conditions. Heavy sleet, for instance. So this is heavy, thick, wet snow. There isn't a sensor on the planet that can deal with that, right? You have things on the road that you don't know what they are. Pianos and debris. You have cars driving in the wrong direction. The point is, there's a lot of strange things that you experience during a 100 million mile journey. And this is why it's hard not to hit stuff. You can train in good conditions not to hit things that stick up and look like things you can expect, but are you going to train on every kind of cow? It's not clear. And this has implications for things like models, right? Because when you're out for long periods of time, long duration autonomy, then uncommon events all of a sudden become common. They are going to happen sooner or later. And that means that we need to maybe think differently about our models. I mean, in controls, or I would argue in almost all of engineering, there are two standard assumptions, like linear systems and normally distributed noise. Well, we need to start having noise models with heavier tails, where we no longer can discard or discount outliers too much, because outliers may literally be the difference between a car crashing or not. And one thing that is certainly true is that we cannot train our systems on everything they will experience during a 100 million mile journey, because the combinatorics of the real world is such that there's a lot of weird stuff that we're going to experience, and we can't just enumerate all of them. And that's why the fundamental problem in assured autonomy of don't hit stuff is yet not a solved problem. So what I'm going to do today is talk a little bit more about long duration autonomy, and in particular how I like to think about it. Then I'm going to instantiate it in a swarm robotics setting. I'm going to be talking about the Robotarium, which is a long duration multi-agent lab at Georgia Tech. And then at the end, I'm going to talk about robots that are deployed in natural ecosystems for long periods of time. And I want to apologize already at this point. I know I'm talking to a distinguished audience of very good controls engineers. I won't be doing that much math in this talk. I'm going to spend quite a bit of time high level and every now and then dive down and show what I think this means technically, but it won't be the let's say theorem to robot ratio will be pretty small in this particular talk, but I do think that there are some really interesting questions for the controls community that will result from them. So let's start. In 2016, there was a paper written by Mark Steinberg. He's a researcher at the Office of Naval Research in the US on long duration autonomy. And in this paper, they identified the three fundamental challenges. What is different about long duration, so deployment over long periods of time as compared to short periods of time? And the first one we've already hinted at. Any attempt at enumerating everything the system might experience will fail. It's impossible. This picture here is actually a robotic swan, and I picked that picture because I have a friend who is a roboticist in France, and he has these robotic boats that go up and down the canals, and they discovered that there was this one location where the boat always failed and was actually stranded up on the or beached on the side of the canal, and they went out and tried to figure out what was going on, and it turns out that there was an aggressive nesting swan living there, and whenever this robot boat came, the swan would attack the boat. You know, it's hard to predict things like that. So that gets to be an example of something that may happen that it's hard to predict. The other thing, and I think this is important as well, is the only way to understand systems that can be deployed over long periods of time is to deploy systems over long periods of time. Because you can't enumerate everything that's going to happen, you need to actually go out into the field. And the reason I picked elephants here is if you want to understand elephants, right? You don't take an elephant, you take it all away from the savannah, you put the elephant in the lab, and you observe the elephant for 5 minutes, and then you say, okay, now I know how elephants operate. Nah, you got to be out there trying to really observe the function and behavior of the elephant in its natural ecosystem or habitat over long periods of time. So we got to be out there. We can't just do lab work if we really want to understand long duration autonomy. And then the third one has to do with optimality. Biomechanics studies have always tried to find what is the cost function by which human beings are optimal. And this is eluding us over and over and over again. And this paper claims that optimality is a pipe dream. So let's not worry too much about optimality. Instead, people are remarkably adaptive and resilient. So we're not optimal in how we walk from an energy point of view, from a minimal jerk or minimum curvature. So that's not how we walk. But what we can do is we can walk upstairs, we can walk in snow, we can walk on grass. Some of us can walk with high heels an entire day without falling over. That is remarkable from a resiliency and adaptation point of view. So maybe resiliency or survival should take a front seat to the normal notion of optimality. So these are three kind of observations. They were made in this paper. I have reinterpreted them a little bit, but basically that's the gist of it. Going back to elephants, this idea is not new, by the way. Rodney Brooks is a very famous Australian roboticist. He was at MIT for a long time, but then he went on and became a robotic entrepreneur. But he has a highly influential paper from 1990 called Elephants Don't Play Chess. And the point with this paper is if you want to build a robot that is going to be as effective as an elephant out in nature, then not falling over and not getting eaten by lions seems to be a higher priority than optimally being able to play chess. So really, the first order of business for a robot that's deployed or an autonomous system deployed for long periods of time has to be this idea of survival. Well, what does that mean for us? Let's go back to the don't hit stuff question. So here are two robots. They're on a collision course, but the arrows are green. And what I mean by that is it's mathematically possible for a collision to be avoided because they could start steering away from each other. So there is a set in the joint state space of these two robots where it is possible not to hit stuff, not for these two robots not to collide. It's possible to do something. Well, outside of this set, it is not possible not to collide. You may not have collided yet, but there's nothing you can do to avoid the collision. This is a structure that shows up over and over and over again in autonomy, where you have sets where good things happen and then sets where bad things happen, right? So don't go unstable, don't run out of battery, don't get disconnected in a distributed communication network, don't get lost, don't lose coverage. These are all problems in autonomy that have the same structure, which really is we want to start in the good set and make sure that we stay in the good set for all times forward in time. So this is the forward invariance problem, right? So if you start safe, and I'm going to call this set the safe set. So if you start in the safe set, you stay in the safe set for all time. That means that don't hit stuff never happens. Okay, so let's see what this means mathematically. Let's go back to the collision problem, right? And what we're going to do here is really reinterpret this forward invariance in a slightly different way, where we're going to say that we're going to minimize what the robots are trying to do and what they're actually doing, subject to this idea that they are not allowed to leave the safe set. And again, this picture, for instance, says the green arrows is the direction they want to go in. It's fine, but sooner or later they will collide if they continue doing that. So for the purpose of this talk, we're going to assume that the robots are control affine. So x sub I is the state of robot I, F would be the drift term, G is the actuator dynamics, and U sub I is the control input to agent I. Now, if we produce a joint state space, then the safe set now, where collisions can be avoided, is this lime green set. And as long as the joint state stays inside this lime green set, we can always avoid collisions. If we're on the boundary, we have to do something. We have to take evasive action. And when we're on the outside of this set, then there's nothing we can do to avoid a collision. And collision may not have happened yet. We may be driving a car towards a wall and going really fast, and we may not have hit the wall yet, but if we slam the brakes, we're not going to be able to prevent a collision with the wall. Now, we're going to assume that this is a super level set to a continuously differentiable scalar function h, where when h is strictly positive, we're in the interior of the safe set. When h is equal to 0, we're on the boundary, and when h is negative, we are outside. So the name of the game then could be the following. At any moment in time, we have a nominal control input. This is what the system is trying to do. This could be the driver steering a car. This could be your favorite controller. This could be a deep neural network. It doesn't really matter. What we're going to do is we're not going to let the robots do U sub nominal. Instead, we're going to say, you get to do U, and we're going to be as close as possible in a least square sense at every moment in time. And then we're going to insist on H being non-negative, because that is safety, right? So this is a problem one could write down, and we could feel good about ourselves if we do write it down. The problem is that we have a cost function and a decision variable that we call u, and then we have a constraint in some other variable that we call x, and we haven't explicitly coupled them in the optimization problem. So this is actually complete nonsense. It looks reasonable, but it is nonsense. And we need to connect x and u in order for this to make sense. And of course, the way we do that is through the dynamics. Okay, so let's connect them. Well, we want x or h of x to be non-negative, greater than or equal to 0. Well, what if it was possible to drive h from some positive initial value, so in the interior of the set, asymptotically to the boundary of the set, meaning asymptotically drive h down to 0? Well, we can do that if we had direct control over h, which we don't. But what if we did, right? Let's say that h dot was negative h. Then we would have an exponential decay. It turns out that we can pick quite a few different ways of driving a function down to 0 asymptotically. Any function alpha that is what's referred to as an extended class k function. So this could be h cubed. It could be some other function. If that was the case, then we would have h asymptotically drive down to 0. Now, what if h dot was greater than or equal to this negative alpha of h? Then by the comparison lemma, which is the gift that keeps on giving in this particular context, if h dot is greater than or equal to negative alpha of h, then the green line, the green trajectory, is going to be greater than or equal to the red trajectory. And the red trajectory is asymptotically going down to 0 from above. So it's greater than or equal to 0 for any given moment in time. That means that the green trajectory for sure is greater than or equal to 0 at any given moment in time. So the key theorem, and variations of this theorem has been around for a while. This particular formulation was Aaron Ames, Jesse Grisel, and Paulo Taboada. It's their formulation, but it goes back in time a little bit further. And the theorem basically says that the set h greater than or equal to 0 is forward invariant under the dynamics if u satisfies, or u is selected such that h dot, which is now a function both of x and u, is greater than or equal to negative alpha of h for some extended class k function alpha. That's the theorem. And what does that mean? Well, let's unpack this. So we want to ensure that h dot greater than or equal to negative alpha of h at any given moment in time. Well, this is just the inner product of the gradient of h with the dynamics. We can formulate this in terms of Lie derivative. So this is the Lie derivative of h along f plus the Lie derivative of h along g times u greater than or equal to negative alpha. Or we can keep the u stuff over on the left and the x stuff over on the right. And what we get is something that looks a little messy, but the decision variable is u, and this is linear in u. What we actually have is something messy as a function of x times u greater than or equal to something else messy as a function of x. But we're going to assume, for the purpose of this talk, that we can measure x and that our models are good. If not, you're going to have to robustify this, and there are different ways of doing it. But the point is that this constraint, the forward invariance constraint, is a linear constraint in u, and the optimization problem then is minimize the distance between u and u nominal squared such that this constraints hold. And this we do at every moment in time. It's a quadratic programming problem, something we can solve blazingly fast, and it ensures forward invariant. So the theorem says that if the input satisfies the constraint, then if the robots start safe, they stay safe. Collisions are avoided. Now, there are no guarantees here that solutions do exist. I should say that already at this point, that the theorem says that if we find a u such that this is satisfied, then forward invariance is ensured. It doesn't guarantee existence of solutions. You have to back that out in other ways. So here's an example of this in action. So we have a bunch of robots, and what we're doing is we're asking them to drive through the same point in the middle and swap positions with each other. So it's basically a robotic car crash. And now, instead, we're saying follow this controller that's driving them through the same point in the middle, subject to don't collide, which we're formulating in terms of these control barrier functions. And what I like about this is that we're not telling the robots how to avoid collisions. Instead, all we're doing is we're phrasing collision avoidance as a constraint, and at any given moment in time, each robot, and in this case, you can do it in a distributed way, each robot is solving a quadratic programming problem, and things like traffic circles emerge naturally. It also works because all robots are playing along, but what if even one robot didn't want to play along? So here we have a big robot that's just going for it, and these poor small robots have to run for their lives. The point is, it's still safe. It's still guaranteed to work, even if one robot is misbehaving. You can also put this in the air. So we did the same thing for quadcopters, and crashing is worse. Those that work with quadcopters, like me, we spend a lot of time picking broken robots up out of the sky. And here, we're now letting 4 quads fly in a circle, and the 5th quad is piloted by Li Wang, who is a former grad student of mine, and he is trying to make the 5th quad slam into some of the rotating quads, and it's impossible because of the barrier function. We did other things. I should point out that Li, after he graduated, went to work on Tesla's autopilot, so this is positive. We also did this with learning systems, where we didn't fully know everything about the dynamics of the system, and we had to discover it over time. By the way, I keep getting these notifications that people are waiting in the lobby. Bing, are you letting people in? Okay,
yes. Yeah.
Cool. So the learning problem there would be that we don't know everything what's going on, so we have to pick a small initial safe set, and as we're learning more about what's going on, we can expand the safe set and be more aggressive in how we experience the world. Again, we looked at quadcopters, where the Euler-Lagrange part of the dynamics we understand perfectly well, but the aerodynamic piece is hard. I'm an electrical engineer. I don't understand aerodynamics. So we had to learn the airflow piece. So what we did is we flew a small quadcopter through one of these bladeless fans, where the airflow was really messing up the robot. And over time, we would expand the size of the safe set. So what you're going to see here is a small quad. It's on the left of the fan, and it's driving through it, and we kept driving through it, and it's not able to hold its position very well. Sometimes it would even fall out of the sky just because we didn't account for the airflow properly. But then, by slowly expanding the safe set, we actually learned how to stabilize properly the quadcopter in the airflow with this forward invariance property. So that, I want to say, is one way of thinking about this long duration autonomy problem, which is to say that there are sets that no matter what the robots do or what the systems do, and we don't know what they're going to do, and we don't want to know what they're going to do. In fact, they're going to maybe learn and adapt over time, but there are certain things, certain sets that need to be maintained in a forward invariant manner for all time, no matter what the system is doing. So let's instantiate this in a swarm robotics setting. So this is a video from my lab from, again, 15 years ago. There are 12 robots. They're asked to, in this case, assemble shapes. By now, by the way, fast forward, and this could be a lot of labs all over the planet. We all know now kind of how to do things like this in a distributed manner. These robots are, we broadcast what the shape is. So for instance, we go T, and then they know they have to assemble a T. They don't know where they're going to go in the assembly. In this case, there's no communication. They only measure the distance to robots that are nearby, and they have to figure out basically how to do the assembly. And the reason why I'm showing this is a handful of years ago, I was walking through my lab, and I was getting more and more irritated about things like videos like these, because there is a whole lot of stuff going on in this video that we're not showing. We're showing robots, and then you saw a grad student show up. Ted Edwards is his name. But the point is, there's also a lot of infrastructure around. There are computers, there are, and I have motion captioning cameras to doing indoor localization. There's other cameras. There's an army of grad students and postdocs standing around. Long story short, there's a lot of this going on behind the scenes that you can't see. And what has happened in the world of robotics is that it's become a resource competition, almost more than a good ideas competition. And if you go to the main robotics conferences, there are only a relatively small number of labs that can compete at the highest level. And that is not because there are a relatively small number of people that can do distributed controls. Well, there are tons of us, right? And I really didn't like this. I fundamentally believe that research should be about who has the best ideas, not who can raise the most money. As a dean, maybe I shouldn't say that, but as a researcher, I certainly fundamentally to my core believe that that is the case. So I set out to solve that. And the solution is kind of obvious once you think about it. What we should do is we should build a robotic lab that other people can use. So we set out to build something that we called the Robotarium. This was at Georgia Tech before I moved to the West Coast. And the idea was really, this is a remotely accessible swarm robotics lab where people can upload code and run experiments remotely on our robots. So I went to the National Science Foundation. They have a program called MRI, which stands for Major Research Instrumentation. And I pitched this idea. In fact, I worked closely with Kishan Baheti. Those of you in the US know that Kishan passed away a year and a half ago, but he was during the pandemic, but he was absolutely critical to the controls world in the US. He's been so influential. And from my point of view, the Robotarium was really something that I developed jointly and together with Kishan. But anyway, this picture here is literally the picture I put in the proposal. This is the Vienna Chamber Orchestra's concert hall with some Harvard kilobot sprinkled in on top and then some random screen thing. And I said, this is what I want to build. And NSF said, good, please do it. And this is what I built. Not quite the chamber orchestra. Actually, this was an early version. We did build something quite elegant. I wanted it to look different because it was supposed to be a highly visible lab where visitors could come. It was always on, and we went live in August 2018. I had looked at some other remotely accessible labs, not robotics labs, but there are labs doing wireless networking. There is a cybersecurity lab out of USC. There have been other attempts. And the number one reason why these labs didn't succeed, or some labs didn't succeed that tried to be remote access, was no one used them. Just because you build a remotely accessible lab doesn't mean that anyone will use them. So we strategically, first of all, begged our friends to use them. The first user was actually Jorge Cortes, who is a faculty member at UC San Diego. And that was just because I really asked him. I needed someone to use it. And he kindly agreed to be the first user. But we did a lot of media. We made sure that we were in a lot of newspapers, on television. We were in the Wall Street Journal, and the front page of the Wall Street Journal said, this robot lab has no idea what its robots are doing, which is absolutely true, because we didn't. People uploaded code, and the problem was we were really not ready for the onslaught or the onrush of users. People started using this right away because I think we did lots of media, and they broke a lot of robots. So what we had to do is we had to go back to what we just talked about and wrap these safety wrappers around the controllers. Minimize the distance between the actual input and the user specified input, subject to don't hit stuff. And we now know what that means, right? So here's the same example that we saw before with robots in the Robotarium that are trying to go through the same position in the middle, but the barrier functions kick in and prevent collisions from happening. I should say this is sped up twice, so it's twice as fast as it were. But what you do when you upload code is, unless you can convince us that they're not going to collide, these safety barriers are running in the background. And what I love about this video is that this is really, really densely packed robots. It's way more densely packed robots than you will see hardly anywhere else on the planet. And it has allowed us to be able to run robots in the Robotarium more or less non-stop for years. The things you see on the side, these are charging stations. So when they're not engaged in an experiment, they just go and recharge wirelessly. And then when they're being recruited, they go back out and they run experiments. So since, it was 2017, not 2018, we've actually had a lot of experiments run. We have a large number of registered users. What makes me happy is we have labs from all over the world running experiments. And that is ultimately what I was interested in, right? I wanted to make sure that people could run real robotics experiments without having to pay for all the hassle that comes with actually maintaining and building a lab. We also have the first paper we wrote about the Robotarium. So it's free to use, but we ask people that if you write a paper and you reference or you use the Robotarium, please reference this paper. And we, with the latest count, have over 250 papers where the experimental platform is the Robotarium. But one thing that we did is we looked at what labs are using the Robotarium. So this is not the nationality of the users, but what individual labs are using the Robotarium. And the vast majority is North America, fine. Asia comes in second, Europe third, maybe no huge surprises there. But then we have a non-trivial South American presence. We have lots of users in Paraguay, it turns out. And then in Africa, there are 3 labs that we know of that routinely uses the Robotarium for their experiments. And I am really happy about that. I mean, yeah, the green slice is much smaller than the blue slice, sure. But we are able to reach labs in underserved pockets of the planet, and that is actually really powerful, I think. I just wish that we had Antarctica here as well. So my request to you is, if you move to Antarctica and you open up a robotics lab, please run experiments on the Robotarium so I can claim that we have every continent of the planet represented amongst our use base. But the point is, I think we've been successful from that point of view. Another surprising aspect of this was what happened during the pandemic. And there is a saying that says, if life gives you lemons, and in this case, COVID lemons, make lemonade. We managed to convince Georgia Tech that the Robotarium was a critical facility. So it stayed open during the pandemic. And we saw the number of submissions really spike around the summer of 2020. And it had held steady at almost 10 submissions per day throughout the pandemic. And what it meant is even people that have robotics labs that couldn't access them had now a way of keep running experiments and keeping the research going, even though we were all sent home in the spring of 2020. We've also seen other domains or other Robotariums pop up. There is a Robotarium West. This is the Robotarium Watchtower camera feed from the Duckytown Robotarium in Zurich. We also have seen federation of remote labs where, for instance, there is a lab at Tokyo Tech that ran experiments at the Robotarium and at Tokyo Tech at the same time across 11,000 kilometers and over a 200 millisecond delay. And that was really cool to see robots across the planet synchronize their activity. So that was another piece of lemonade that we didn't expect. But from my point of view, this is a long duration deployment that proves that something like this is possible, because the Robotarium has been in continuous operation for years with minimal to no human intervention. Every now and then we do have to step in, and we stepped in when we upgraded the robots. We had to step in and replace a robot that broke, but more or less we've had no intervention over years, and that is quite remarkable, I must say. So that's an example of how one can think about this long duration autonomy idea with forward invariance in the context of swarm robotics. So now I want to go to the last area, or the last part of my talk, and this is slightly more speculative. You should pay attention to the first two pieces. This you may pay attention to, but it's softer technically, and that's the question of, well, maybe we know how we should do long duration autonomy now, but what should the robots be doing? If I want to deploy robots in the snow with Bing in Southampton, what for long periods of time, what should they be doing? Not how should they do it, but what should they be doing out there in the snow? Let's say I want to know what's going on on campus there in Southampton. Should the robots form circles, or should they form squares? What kind of geometry is better? What should they do as the seasons change? In the world of robotics, particularly in multi-agent robotics, which is my area, we've drawn a lot of inspiration from nature. We've learned a lot about how to think about things like formation control by looking at how fish school. So why not ask the question, if you put robots out in the snow for long periods of time, why not learn from other things that are out in the snow for long periods of time? Here's an Arctic fox, but let's look at ecology. Let's see what we can learn from people that study organisms in their natural habitats. Now, I'm not an ecologist, but I have started to work closely with ecologists. I've given talks at ecology conferences, and I've taken ecology classes. So let me tell you a little bit about what I've learned. And I'm going to explain to you what I've learned about ecology by doing an experiment. We're going to build an animal together. And the animal we're going to build is what's called a folivore. Means this is an animal that eats leaves. Now, leaves are really complicated foods. They are structurally protected. They have these really thick fibers. They're also a lot of times toxically protected, which means it's hard to break down this horrible food. What that means is that folivores, they need to have a long digestive tract to break down this food. A big gut. They need to be big. Elephants and giraffes and cows have multiple stomachs. So they need to be big to break down this horrible food. By the way, plants, they have fruits and nuts. Those are high energy sources. Perfectly happy to have those be eaten. But leaves, no, they're power plants for the plants, right? That's why they're a lot of times technically they're protected. So big animals if you're going to be a pure folivore. But I also want this animal to be arboreal. I want the animal to live in the trees all the time. And it's rare to see big animals living in trees all the time because, you know what, they're too heavy. They fall out of the trees. So now I have an extremely tight ecological niche. I need to be big enough to break down this horrible food and small enough not to fall out of the tree. And it turns out that amongst mammals, nature has solved this problem, but only a handful of situations. So here we have a three-toed sloth on the left. There is also a two-toed sloth. The animal in the middle is a slow loris, is a primate. You have a koala on the right. There are a few lemurs that also are arboreal folivores. They are all more or less the same size, this big, 3 to 8 pounds. And they all also more or less never move. They just sit there digesting this complicated food, and they spend all their time not starving to death. And since I was interested in deploying robots for long periods of time, I was very fascinated by animals that have what's called low energy lifestyles. And in particular, I started reading up about sloths. And I got fascinated with three-toed sloths because they spend more or less their entire lives in 1 to 2 trees. That's their ecosystem. But the male sloths, every now and then, every 2 weeks or so, they're sitting up there, and then they would climb down the tree and go to the bathroom and then climb back up. And this makes no sense whatsoever. It's energetically the most costly thing the sloth will do. I read someone describe this as the sloth running a marathon in order to go to the bathroom. It is also by far the most risky and dangerous thing a sloth will do. And in fact, the same paper said that it's like running a marathon while being attacked in order to go to the bathroom. So why would the sloth do that? Well, at this point, I'd started working with John Powley, who is a sloth ecologist. And I asked, why do the sloth want to climb down the tree to go to the bathroom? And John told me That is the wrong question to ask. An ecologist never asks why an animal wants to do something. An ecologist always asks, what are the constraints imposed on the organism by the environment that makes this behavior emerge? So biological diversity and richness of behavior are largely driven by constraints. So constraints is what makes animals do things, is what John more or less told me. And me being a controls person, I immediately said, oh, I know what this means. Minimize energy subject to don't die. That's ecology. And John looked at it, John Pauli, the ecologist, and he's like, yeah, if you take mating out of the equation, because mating behaviors are a little weird, but if you take mating out, this is pretty good. So don't do anything subject to don't die. It's a little depressing. It's existential nihilism. Life is meaningless. We should just be sitting on our couches and every now and then go to the fridge to get a snack, but that's pretty much it. But that's something we now know how to deal with, because we know how to deal with constraints. And minimum energy, well, that's min u squared. We know how to do that. So why don't we put this, we tell the robots that we deploy, don't do anything subject to don't die, meaning constraints that somehow encode longevity. So let's see if we can turn that into something that we can actually deploy. And I'm going to do it in the context of environmental monitoring. I have gotten to a point in my career where, first of all, I think that there's one question that's more important than any other question we're facing as a global society, and that's how do we leave a planet for our grandkids that's not burned to the ground? And as a controls and robotics person, can I do something to help here? And to me, environmental monitoring is one area where we can contribute. So I've been interested in building robots that are out figuring out what's going on with the climate, either the macroclimate or the microclimate. This has been done also in the past, right? There have been robots down counting penguin colonies. There's a lot of marine gliders out looking at pollutants in the ocean. You know, the wonderful Mars rovers, Spirit and Opportunity, they're environmental monitoring robots because they're trying to figure out what the environment actually is like on Mars. Is there water there or not, right? So that's the application domain that I am interested in this particular context. It's closely related to precision ag, where the idea is that you have robots out in the farm fields or in the orchards over truly long periods of time, tending to individual plants. So instead of bombing the fields with water or pesticide or fertilizers, you have robots that can be out there moving slowly up and down the aisles or the corn rows, tending to individual plants. So that's the context. Fine. And in particular, if we're doing something like environmental monitoring, let's actually look how nature approaches this itself, right? Because we've already started to embrace nature big time. Over on the left, this is a picture of the distribution of lion prides in Tanzania, and they form what's called power Voronoi tessellations, where there are more densely packed lion groups or prides if there is water or lots of prey there. So you basically get a density function distributed over that area, and then they actually form more or less Voronoi cells for the different prides. There is a famous paper by Hamilton from '71 called The Selfish Herd that shows that it's strategically advantageous both for individuals and the herd itself if everyone moves to the center of their own what's called region of dominance. Again, a Voronoi tessellation kind of idea. And on the right, you see termite mounds. These form what's these distinguished hexagonal patterns. Well, Voronoi tessellations. So why don't we do something like that, where you want to cover an area, and that's something we know how to do, coverage control, right? So if I want to minimize U squared subject to don't die, we can interpret don't die in the environmental monitoring context as follows, which is don't collide with other robots and stuff that's out there, and always have enough, should be energy, to return to a charging station. This could either be an artificial charging station, or it could be go out from under the trees and recharge your solar power, but you shouldn't be caught in a cave with depleted batteries. So don't collide, and always have enough energy to return to a charging station, and either cover a big enough area with your monitoring sensors or recharge the batteries. That's what we're interpreting "don't die" to mean in the environmental monitoring context. Now, there are ands and ors here, so we need to be able to do Boolean composition. There's a lot of technical stuff that goes in there. And and or turns into min and max operators, and min and max are non-smooth operators. So the second you write this down, you actually have to do non-smooth barrier functions. I'm not going to talk about it in this talk, but this innocent-looking orange square actually has, generalized gradients in it, and ways of making sure that the analysis, this barrier function analysis, still holds for non-smooth operators or non-smooth functions, but it works. So here's what this would look like. This is the old Robotarium, right? We're going to tell these robots, do nothing, subject to don't die, and we now know what don't die means. The charging station is the strip that you see over on the left. That's a charging strip, so that's where the robots have to go. And we're going to speed this up because most of the time these robots don't do anything. So they spread out because they have to cover a big enough area, because that's what the constraint "don't die" means. But the goal is to do nothing, right? That's the objective function. And as you saw, we sped it up significantly, and then the robots in the fourth quadrant is low on batteries, so it's moving towards the charging station. It's going to push one robot out of the way a little bit with the collision avoidance, and then it's going to recharge. The other robots go out and cover the area. Then another robot is going to go and recharge, and so forth. And what's remarkable about this, again, is that this is pretty complex behavior that we're seeing. And so this is the battery levels encoded through voltages, and we're always staying within the allowable band, in theory, indefinitely. So long duration, we told the robots literally min u squared, and this is x dot is equal to u. So don't do anything, subject to don't die, that now had a particular interpretation. And in fact, I got so excited about this idea of using constraints to drive behavior as opposed to goals or costs, that my pandemic project was, I wrote a book that I called Robot Ecology, Constraint-Based Design for Long-Duration Autonomy, with the idea really was, can we revisit a lot of the classic robotics questions from a constraint point of view as opposed to a goal-driven point of view? And it turns out that the answer is yes. You can do a lot of robotics through constraints. Not all, but a lot. Not only that, now, since we started with sloths, we need to build sloth-looking robots. So we started building the Sloth Bot, which is a cable-driven robot for monitoring what goes on up under the tree canopy. So this was an early version of the Sloth Bot that we worked on together with a professor at Cornell. And the idea was that this thing would, be able to climb up these wires, sit under the treetops, monitor the microclimate, things like carbon dioxide levels and humidity, and every now and then go out and recharge. This is what it ended up looking like. So this is the Sloth Bot that we see also on the cover of the book. We deployed it in the Atlanta Botanical Gardens in Atlanta. They have what they call a canopy walk, where you're walking up amongst an elevated walkway amongst the treetops, and then over somewhere amongst the trees, the Sloth Bot is sitting. It's sitting on a wire, measuring microclimate data. Most of the time, it's doing nothing, as the theory dictates, and every now and then it goes out from under the trees and recharges the batteries and sunbathes. And we had this robot deployed there for over a year, and it was really quite remarkable to see. People got very excited about this robot that did nothing, and hashtag SlothBot started trending on Twitter, where people claimed that they had seen it move. Sometimes it was just the wind, but the point is, this robot was out there doing useful environmental work for over a year, and most of the time it didn't do anything, because that's what the theory told it to do. So if I take a step back, what did we do in this talk? Well, it was really an assured autonomy and long duration autonomy talk. And here is how I like to think about this problem now moving forward. I have my system. This could be a self-driving car or a robot on a wire or something else. So you have the system. What a controls person will do, what we do in our first controls classes, right, is we teach our students how to stabilize it. So we design a stabilizer controller using feedback, basically change the behavior of the system. And a lot of times students leave our first controls class thinking that all controls people do is stabilize systems. But there's a reason we stabilize systems, right? It's bounded in, bounded out, because once we have a stable system, we can make the system do interesting things, right? We can have an input that's, this could be new set points, or it could be a person with a joystick driving a robot. It could be the pilot in an aircraft, right? So that's why we stabilize systems. Because without it, we wouldn't be able to make these systems do more or less anything interesting, or less interesting things, right? I think in the world of machine learning and AI and deep neural nets, that's how we should think about assured autonomy as well, right? So instead of saying stabilizing controller, we have our system, and then we wrap that around a runtime assurance. This could be the quadratic programming problem that we saw with barrier functions. You could do it in other ways as well. But instead of saying it's only stabilization, it's now, invariance of safe sets. And now we have an assured system that we can tell to do something. This could be the people that are telling the Robotarium to do something, or it could be a deep neural network in a self-driving car that over time is telling the car to do other things. Well, the runtime assurance is still allowing the learning system to do something interesting, but the guarantee happens at the lower level. And this is how I've started thinking about assured autonomy more broadly. There are people that are looking at other approaches, but from a controls point of view, this is such a natural way of viewing this whole problem of how do we build systems that are deployed for long periods of time, that evolve over time, and that we can fundamentally trust. Okay, so with that, I want to say thank you for listening to this talk. It had few different pieces. The long duration autonomy problem, I think, is really a fascinating problem because it is different. The control design is different, where survival is more important than optimality. And I think as controls people, this is a rich area for us to be working in. I should also say that a lot of this work, in fact, virtually all of it, was done by students or postdocs in my lab or collaborators. So if there was something you enjoyed in this talk, I strongly suspect that it was due to someone on this slide. And if there were things you didn't enjoy in this talk, I suggest that we blame the organizers, Tiago and Bing, for inviting me to come and give this talk. Thank you.
Thank you, Magnus, for the presentation. I think it was great. We had the opportunity to see many of the applications that you are working on, and so they are fantastic. So, and the end with the book, I think we complete the package. So this is a good opportunity to us to check your achievements. So we have some questions here. I think the first one is from Emilia. Maybe Emilia wants to provide the question by herself. Emilia, where are you? You are muted.
Still muted, Emilia.
Bing, maybe you can unmute her.
No, I can't.
Emilia, I think your microphone is
in
So Emilia did put a question in the chat.
Yeah, she did it. She was asking about.
No, okay.
Great.
Sorry. Okay, so great talk, Magnus. Thanks a lot. Happy New Year to all of you, of course. And I'm wondering how long-distance users of your Robotarium managed with communication delays? This is my
Yeah.
talk.
So that's an important question, right? So the way regular users of the Robotarium use the Robotarium is you upload code. There is a queue, and it's a first in, first out. And then when it's your turn, the controllers and the code you uploaded runs locally at the Robotarium. So regular users, it's not a remote controlled thing. Instead, it's a way of uploading code and running experiments. But for example, the Tokyo Tech experiment, where people literally ran it across significant delays, their experiments they were explicitly trying to investigate how passivity and scattering transforms and dissipacivity could be used to make sure that these systems remained passive and didn't go unstable. But the way we solved it is, and this was also from a cybersecurity point of view, we ended up having to solve it by having people upload code and then running the code locally as opposed to remotely. So we didn't solve that problem. We shortcutted that problem.
Okay, thank you. Hi, Miroslav.
Hey, by the way, great to see you, Emilia.
Thank you.
Thank you, Emilia. Miroslav raised the hand. You're the next, please.
Thank you. Thank you. Magnus, thank you for a fascinating talk. I didn't know about your book. I cheated a bit and looked up the table of contents, and I see this is something I should own. I must get, and I will. But I did not get past the table of contents. And as you were speaking at the beginning with the examples of totally unexpected things that an autonomous user might encounter, the thoughts that come to mind are the thoughts about robustness, about robust safety, about safety of the input to state safety kind, where, well, you must tolerate some violations and some collisions as long as they're mild. But we are actually in a learning TC setting, so I should not be asking you those robust questions, but it should be something about learning. So as a system operates over a very, very long time, one sees two conflicting possibilities. One sees the system encountering over a very long period of time lots of possibilities from which one can learn. I mean, not learning, but using simply robust control in a long-term operation is simply silly. On the other hand, those of us in adaptive control know that in a long-term operation, where you're mostly encountering normal circumstances, you get so biased towards the normalcy that attempting to do something on the basis of learning can make things even worse. You know, a decade was spent on robust adaptive control to resolve things like that. So if you have some thoughts on learning in the context of this long-range autonomy, be it the learning of CBFs or learning in the feedback law, I do see it mentioned in your table of context. So I'm sure that you've given some thought to this.
Yeah, absolutely, and I think you hit the nail on the head very much in terms of, if you're running a normal type of learning algorithm and the vast majority of the time you're just experiencing the same stuff over and over again, you're over biasing on the stuff that isn't that hard to manage, and you're missing these uncommon, but in a long duration setting, still common events. One of the things that I did towards the end is I wanted to somehow separate out the learning. There is a learning piece, but then there is an inner loop that has to assure the integrity of the system. And I actually think learning CBFs is a very promising way forward. And what I showed with the quadcopter going through the fan, that was just one small example of this idea of allowing yourself to become more daring over time as you're learning more and more, and you have to start conservative. But I genuinely think that in the long duration setting, robust adaptive control still is extraordinarily important, because that is a way of managing uncommon things and managing sets rather than distributions that tend to pull you towards the center of the distribution. When I said I had a bullet that said outliers cannot be discounted / discarded, it's exactly me trying to articulate that. So I think this idea of separating what people that are deep in the deep neural network world, and they're really good at learning stuff, but it's very hard to trust it, that happens outside of the inner loop that does assured autonomy. And there we should be learning things like barrier. And in fact, that's how I do it. I try to either learn the dynamics or learn the barrier functions, or both. And that's, I mean, a lot of people are going down that path, but I actually think there is a huge opportunity for this particular community, or our particular community, to have something important to say here. So I'm just going to be quiet.
Thank you. Thank you.
Thank you, Miroslav. I think we have a question from Rubens. I'm not sure if Rubens wants to ask directly to Magnus. If yes, just open the mic. So the question, my mic is not working. Okay. Thanks, Magnus. Reducing the problem to a QP seems fine, he says. My question would be how to deal with the infinite dimensional problem. You solve for instantaneous U that makes dHdt less equal to minus alpha, but this would require solving QPs in continuous time. Is there some discretization scheme?
Yeah, so by the way, I'm glad you caught that, right? Because the way I formulated it is in continuous time, and then anything that's implemented has to be implemented in discrete time. And since we're all amongst friends here, the way I do it is I sample fast enough and hope for the best. There is a discrete time version where there are discretization schemes out there for barrier functions, of course, right? Not surprising, but the overhead tend to be more than I'm personally interested in, but then I'm sacrificing some of the, when I came out swinging and said we need to trust these systems, and here I'm just hoping that I'm sampling fast enough. I happen to have another view of the world, which is models are fables. Models are not the real thing, right? And we're always making some assumptions about something whenever we commit to a model. And ultimately, we want our models to be rich enough to capture what it is that we're interested in, and simple enough so that we can actually do something with them. And that is the magic of a good model. And, going back to the world of linear controls, right? We know that there isn't a linear system anywhere on the planet. But when we use feedback, for instance, all of a sudden, nonlinear systems, if we linearize them and then close the loop, all of a sudden they start behaving as if the linearization was okay. So what this was my long way of saying, this is one area where I'm saying that for me, this has worked as an approximation, just sampling fast enough. There are discretization schemes that I haven't gone down just because it doesn't seem worth it to me. But if you really want to work on it, one needs to obviously do the discrete control correctly, as opposed to what I do, which is I sample fast enough and hope for the best. So you got me there.
Thank you, Rubens. Thank you, Magnus, for the answer. Bing, do you have some question?
I have a very quick one, Magnus. When people use your platform and upload code, do you do a pre-check in any way?
Yeah, so we had this ambition when we started that we were going to do formal verification of the behavior of the code. We ended up giving up on that because it took too long. So what we have is we have a simulator, and the simulator is exactly the same as the code you run on the simulator is the same as the code you run on the actual platform. It's just a flag that says, are you going to run it on the simulator or on the platform? We ask people to run the code in the simulator, and then what we do is we take the code and we run a snippet in the simulator and make sure it doesn't break. We don't know if it's good control design. We don't know if the robots do anything meaningful, but we do a short run in the simulator automatically to make sure that, you know, nothing was, there's no syntax error in terms of the programming, but that's the only check we do. The one thing that we were really nervous about, and I should say, this is not, you know, robotics or control design. One aspect of starting early was, when we started, was people started trying to take down the Robotarium as well. There is a whole bunch of bad people out there that just think it's fun to try to hack into things like this. So the other reason we're taking code, moving it onto another machine, is as a way so that people can't directly interface with our machine. So that was our solution also from a kind of cybersecurity point of view. People aren't nice on the internet, or there are people that aren't nice on the internet.
Thanks. Thank you.
Magnus, there is another one here. José Franco from the same university as me would like to ask directly, Franco.
Hello, Thiago. Do you hear me?
Okay.
Yeah.
Yes.
Okay. Yeah. Thank you very much for the invitation, Thiago. I really enjoy. Many thanks to Professor Magnus for the amazing seminar. My research is focused on agriculture and precision agriculture. So here in Brazil, progressively necessary to optimize crop yields. So many robots are in use today. So I'd like to hear from you about these robots in agriculture, long-duration autonomy, because of course, a lot of strange and unpredictable things happen on the crop yields. So many animals and non-predictable things happens, and well, the robots go crazy.
Yep. Yeah, so first of all, I completely agree with you that it's not just in Brazil, right? That if we're going to be able to feed a growing planet, and we're going to be able to manage our natural resources more effectively, we have to go to a precision agriculture model. We can't think of these big fields as just being one thing. We also can't drive really big and heavy tractors up and down the fields indefinitely, because of you compactify the earth, you do all sorts of things that have significant, you know, environmental footprint. So this is an important question, and I actually think from a robotics point of view. So I straddle both fields, right? I'm a controls person, but I also go to a lot of the robotics conferences. I worry that we're looking at things like urban air transport and how do we do flying taxis before we figured out how to do precision ag, because I think precision agriculture is a more important problem. I also think in many ways it's an easier problem, because yes, there are strange things happening out in the fields, but there are more strange things happening in cities, right? And but there are animals and there are things. I should say, so the only I've worked on two types of agricultural robots. I've done self-driving tractors together with John Deere, and there it was, you know, it was still tractors, so they were these big things still, and didn't have to worry too much. It was just going up and down. But then we have a smaller version of the Sloth Bot that's looking at vineyards, and there, you know, the vines are actually, you have the wires already there, so we could just have the robot go up and down there. But that lifts the robot up away from the ground, because the ground is complicated, and I think a lot of the weird stuff that you're talking about are ground-based things. And ground. So all I'm going to say is yes, I think we need to figure it out. I don't know. I've avoided the ground just because it's hard. There, it's not so much a matter of can we prove theorems about forward invariance of sets. It's still the kind of basic, how do we know what it is that we're seeing, and how do we make sure that the robot doesn't get stuck in the mud after rain and things like that. And I think that's almost more of a kind of technology question more than an adaptive controls question, I would say at this point. So my answer to your question is it's a really good and really important question, and I wish I had better answers.
Oh, that's a great answer. Thank you very much.
Thank you.
Thank you, Franco. Thank you, Magnus. Any other question to Magnus? This is the time. We have some comments in the chat thanking you about the talk. You can read this directly from Alessandro, Boris, and some other guys.
Yeah, I'll read it, and I appreciate it. So thank you for saying nice things in the chat.
Yeah. So Magnus, thank you very much. I think we can. Fabrizio has one. So Fabrizio, go ahead.
Oh, Fabrizio.
Hi Magnus. Hi Thiago. Hi everyone. Are you hearing me?
Yes.
Yeah. You really have plans to extend the Robotarium lab to underwater environment or outdoor environment?
Yes, I really want to do so. When we started the Robotarium, I call it the Roboquarium because I imagine it being like an aquarium where you looked in and you could see the robots and it was be glass. And then I realized, of course, there's no water, so it's a terrarium, so the Robotarium. That's how that name came up. I want to build a Roboquarium. I would love to have an aquarium for robots. This is still I'm started building an indoor version of it. Because outdoor marine robotics is really hard, and I've lost robots underwater. They just take off and they never come back. The Robotarium is focused on highlighting particular things, and in particular, what this version of the original Robotarium, it is highlighting distributed controls, right, and distributed mobility in some sense. It's not a sensing platform really. It's it's not doing advanced anything from that point of view. I think the Roboquarium would still be kind of looking at what happens underwater, things like communication issues, I think. But the really hard problems in marine robotics, I'm not going to tackle with the Roboquarium. I wish that someone else would do it because marine robotics is hard. It is hard just because when something goes wrong, it's hard to get the robot back. But maybe we build one in Fortaleza instead, no?
Yeah, sure. We are looking forward to see it. Thank you, Magnus.
Thank you, Fabrizio. I think this is a good idea because Miroslav maybe can say something about the source-seeking algorithms. He has a very interesting application on fish locomotion going through the direction of the source. So it will be great to have something like this. Yeah. So guys, I think there is no other question. So we can close the session. Thank you again, Magnus, for your presentation. It was very good.
I want to say
to be here, yeah.
And thank you so much for the invitation. This was great.
Yeah, thank you guys. See you next month. I think I will say an email to you about the next speaker, and Sam can continue. I'll give the same information to you, Magnus, so you can follow that. So okay. See you guys.
See you.
Thank you.
Have a great day. Bye-bye.
Bye.
Bye.
Bye, Bing. See you.
Bye-bye, Thiago. I'm waiting for all to leave, then I can close the meeting properly.
Oh, yeah, for sure.
Yeah. Bye-bye. We'll be in email contact shortly. So.
Yes, sure.
Bye-bye.